In this video, we are going to learn the counting principle. That's our ultimate goal. So let's start off with an example. List the elements in the sample space S of the experiment. Here's our experiment down here. And then we're going to count the number of elements in the sample space S. So the experiment is that we randomly select an even integer between -6 and 6 inclusive. So that just means including -6 and 6. So if I were to randomly select an even integer between -6 and 6, what are all the possible outcomes? So that's what the sample space is. It's the set of all possible outcomes. Okay, so the set of all possible outcomes in this experiment is S. Well, I could select -6, -4, -2, 0, 2, 4, or 6. Okay, so in this case, there are 1, 2, 3, 4, 5, 6, 7 outcomes. 7 possible outcomes. So let's do a second example. So again, we're going to list the elements in the sample space S, and then we're going to count the number of elements that are in the sample space S. So the experiment in this case is we toss a coin 3 times. So for example, I toss the coin the first time and I get a head. I toss the coin again, and let's say I get a tail, and then I toss the coin a third time, and let's say I get a head. So this is one possible outcome. So what are all the possible outcomes when I toss a coin? So something that might help you is to think about this in stages. So the first stage is I toss the coin the first time, right? And there's 2 possible outcomes, right? I could get heads or I could get tails. So I think about that as stage 1, my first toss. Next, I toss the coin for the second time. And I could, once again, on the second toss, I could get heads or I could get tails. If the first toss was a tail, same deal. I could get heads or tails on the second toss. So I think about this as stage 2. This is my second toss. Finally, the third stage, I could get heads or tails on my third toss. So I'm just going to write out all these possibilities just to keep track of everything that could have happened. And this is, I'm going to call this stage 3. So this is my third toss. So this is how you can visually see all the possible outcomes. I'm just going to read off each possible outcome. So I could have gotten a head, and a head, all 3 heads. I could have gotten a head first, then a tail, or then I could have gotten a head first, a head second, and then a tail. So this is heads, heads, tails. I could have gotten a heads first, tail second, and heads third. So this would give me heads, tails, heads. Or I could have gotten 3 tails. And so here you can see we have 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes. So this is my sample space. So here you see the sample space S, and if I count the number of elements in S, you can see there are 1, 2, 3, 4, 5, 6, 7, 8 elements. Okay, so I've answered both questions now. The object we have here is called a tree diagram, and it just helps us to list the different possible outcomes for an event with multiple stages. So stage 1, stage 2, and stage 3. Another thing I wanted to point out that I want you to note is note that 8, the number of elements in the sample space, is equal to, the following. So if I look at the first toss is stage 1, there were 2 possible outcomes in stage 1. And if I look at stage 2, once again, there were 2 possible outcomes, heads or tails. And finally, if I look at stage 3, for each of these, there were 2 possible outcomes, heads or tails on that third toss. So note that the total number of outcomes in the sample space S, which was 8, is equal to 2 times 2 times 2. So let's do another example. Again, we're going to list the elements in the sample space, and then we're going to count the number of elements in the sample space. So in this experiment, I randomly choose a digit between 1 and 3 inclusive. So that's 1, 2, or 3. I'm going to randomly choose one of those 3 digits, and then I'm going to toss a coin. So again, this experiment has 2 stages. So you can think about this as stage 1. First, you're going to pick your number, and then stage 2 happens, we toss a coin. So let's think about that as stage 2. So first, so if we were to make the tree diagram to help us understand what's going on here, I'm first going to write down, okay, what are the possibilities when I select that number? I can get 1, I can get 2, or I can get 3 in stage 1. And then I toss a coin. So what are the possibilities? Heads or tails, right? So if I had a 1 first, the possible things that could happen in stage 2 are heads or tails. Same thing here and same thing here. So this helps me to list all the possible outcomes. So S, in this case, our sample space, is equal to, I'm going to write this down. The first possible outcome is 1 with an H, or we can get a 1 with tails, and we can get a 2 in the head, or a 2 in a tail, or a 3 in a head, and then a 3 in a tail. So that is every single possible outcome. And how many elements? If we count the number of elements, we get 1, 2, 3, 4, 5, 6. And again, I want you to note something special here, and that's that 6. We can think about this. So if we think about in the first stage of the experiment, in stage 1, there were how many? 3 possible outcomes. And in stage 2, for each of those stages, when we toss a coin, so stage 2, we have 2 possible outcomes. And if I multiply 3 times 2, I get 6, which is the number of possible outcomes in the sample space for the original experiment. And so we want to generalize this result, and it's called the counting principle. And basically it tells us that the total number of possible outcomes in our sample space is given by the number of outcomes in stage 1 times the number of outcomes in stage 2 times the number of outcomes in stage 3, etc. However many stages you have. The one way we can determine the size of the sample space is to just look at the number of outcomes in each stage of our experiment and then just multiply them. So we're going to do some examples now. So use the counting principle to determine the number of elements in the sample space. So 3 numbers are selected without replacement from the natural numbers 1 through 97 inclusive. So there are 97 numbers here. And without replacement means that once I draw a number, I don't put the number back before I draw the second number. So for example, after I draw one number, there are only 96 choices left. Okay, so let's use the counting principle here. So there are 3 numbers, so we're going to have 3 stages. Okay, the first stage is when we draw the first number. The second stage is when we draw the second number, and the third stage comes when we draw the third number. So in the first number, how many different possible outcomes are there when I draw that first number? Okay, well, there's 97 numbers, so there's 97 possible outcomes. Once I draw that number, it's without replacement, so I don't put it back. And then I go and I draw the second number, and in that case, the number of possible outcomes is only 96 because I've already used one of the numbers over here. And then finally, I draw the third number, so that's my third stage, and there are only 95 numbers left. So by the counting principle, I multiply these 3 numbers, and I get 888,640. And so this is the number of different ways I can draw the three numbers without replacement. And I just want to point out that, for example, one possibility is I could draw 63 first, and then 22, and then, maybe the number 5. And so I'm assuming order matters, so that I would count this differently from 5, 63, 22. So these would constitute two distinct choices. So we're going to do another example, and this one is very similar to the previous one. So we're using the counting principle again to determine the number of elements in the sample space. So in this case, we have three numbers, and they are selected. Now they are selected with replacement from the natural numbers 1 through 97. So in this case, once I draw the first number, like let's say I'm drawing from a hat, I'm going to put that number back in so that it can be drawn again. So, for example, I could draw the number 22, 22, 5. That's a possibility because this is with replacement. So the 22 that I made on the first draw gets put back in and can be selected again as the second number. So again, we're going to use the counting principle, and I see this as 3 stages. Select the first number, select the second number, select the third number. So how many choices or how many different possible outcomes do I have for when I select that first number? And there are 97 numbers. And since I place that number back and when I make my second selection, I also have 97 possible outcomes for the second number and 97 for the third. So my answer here is 97 cubed, and that is equal to 912,673. So you can see that when we do things with replacement, there are more possible outcomes in the sample space. So let's do an example. So using the counting principle to determine the number of elements in the sample space, how many possible ways are there to complete a 10-question multiple choice test with each question having 5 possible answers? So this can be done with the counting principle if you think of each question as a stage. So I would think about this as this has 10 stages. Okay, so the first question is like stage 1. The second question is stage 2, etc. So, for example, let's say we started, let's look at stage 1. So question 1 is stage 1. And how many different, what is the number of possible outcomes to stage 1? And, well, each question, we're told, has 5 possible answers. So there's 5 possible answers you could have in stage 1. So that's 5 possible outcomes. Same thing with question number 2, or we can think about it as stage 2. The number of possible answers is the same, still 5. And we can keep going like this, right? Each question has 5 possible answers all the way down to the 10th question. And so what do we get if we multiply 5 times 5 times 5 times 5 10 times? We can write this as 5 to the 10th power. And if you pop that into your calculator, you 9,765,625. And if the number just gets to be too big, you can just enter it like this in WebAssign. So here's our final answer. Okay, here is another example. 3-digit natural numbers are formed with replacement from the digits 0 to 9. How many 3-digit odd numbers are possible? So a couple things I want to make clear is that a 3-digit natural number should have a number that's non-zero in the hundreds place. So for example, we need numbers like 321, but I wouldn't count a number like if we were to draw 0, 5, and 6, this would not be a 3-digit number because it's really just equal to 56. So we're looking essentially for numbers that are greater than 99, right? Another thing to note is that a number is odd when it's, a 3-digit number is going to be odd when the number in the ones place is odd. So that's something to look for. So if I have a 1, 3, 5, 7, or 9 in the ones place, then the number will be an odd number. Equivalently, if this number is even, then my whole number will be even. So let's get back to answering this question. We're going to use the counting principle, and I'm going to think of each digit, drawing each digit as a stage. So the hundreds place, the tens place, and the ones place each constitute a stage here. So how many different possible outcomes are there in the hundreds place? Well, remember, this place can't be 0. It can be any of the other numbers. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9 non-zero numbers in the hundreds place. So that will give me a 3-digit number as opposed to a 1-digit or a 2-digit natural number. How about this, the tens place? How many possible outcomes are there in the tens place? Well, the tens place can be anything, right? There's no restriction, so I'm going to leave that as a 10. And how many possibilities are there for the ones place? Well, we can only have 1, 3, 5, 7, or 9 because we were told that the number has to be odd. So there's only 5 possibilities here. So stage 1, the hundreds place has 9 possible outcomes here for that stage, 10 for stage 2, and only 5 for stage 3. So using the counting principle, there's 450 different possible 3-digit odd natural numbers. Okay, so let's do one last example. And in this example, a state lottery consists of choosing one card from each of the 4 suits in a standard deck of cards. Count the number of elements in the event of choosing a 2, a 3, a 4, and a 5. So how many different ways can that happen, that if I choose one card from each suit, that I end up with 1, 2, 1, 3, 1, 4, and 1, 5. So in case you forgot, here is what a standard deck of cards looks like. So here you see we have the clubs. Oops. Here you see we have the clubs, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 clubs. And so you can see that there's an ace, and then we have the numbers 2 through 10, and then we have the jack, the queen, and the king. And then we have the spades here, so this is another suit. And then we have the red suits, so we have the hearts here, and we have the diamonds. So this is a standard deck of 52 cards. Okay, so the question is asking is how many different ways could we get a 2 if we draw one card from this deck, from this suit, one card from this suit, one from this suit, and one from this suit. How many different ways are there that we could get a 2, 3, 4, and a 5? So for example, I get the 3 of clubs, and then the 2 of spades, and then the 4 of hearts, and the 5 of diamonds. That's one way that could happen. But it could also happen if I got the 5 of clubs, the 4 of spades, the 3 of hearts, and the 2 of diamonds. So obviously there's more than one way that it can happen. So how many different ways can it happen? So again, let's use the counting principle, and I can think of this as 4 stage. So I draw from the first suit, and then I draw from the second suit, and then I draw from the third suit, and I draw from the fourth suit. Okay, so and then I'm going to use the counting principle. So let's suppose I take like the first suit, like the hearts. How many possible outcomes are there that match this event of getting a 2, 3, 4, or a 5? Well, there's 4 cards, right? So there's 4 possible outcomes in this first stage. Okay, and then I move on, and I've chosen my card, and I move on to the next suit, and I pick a card. How many different outcomes in this second stage, in the second suit, would satisfy this event? How many different possible outcomes could there be? Well, if I already picked one of the numbers here, it's like I'm choosing without replacement. because I can only have one of each of these. So in that case, there's only 3 possibilities left. And then I move on to the third suit. And now I've picked 2 of these cards. Like, so for instance, maybe I already chose the 3 and I chose the 4. So the only possibilities for the third suit would be like 2 or 5, right? So there's only 2 possibilities left after these 2 stages. And then finally, when I finally get to that 4th suit, there's only 1 card left. So that's completely determined. So the final answer would be 24. There are 24 different possible outcomes.